club of the semester. I encourage you to be there. I want to be talking, and I want to be showing you some interesting math tricks where you can wow your friends with any bar bets. It'll be just kind of a fun, amusing little talk. So be there if you can. So today what we're going to do is I'm going to do a lot of examples today. I think examples are very important. What kind of bedrock for understanding this. It's good to have examples kind of at the fingertips to help you out. But first, I'm going to give you a couple of definitions before we start looking at some families of examples. And this first definition is, I ended with part one last time. Let G be a group. The order of G, if you hear that terminology, the order of G is the cardinality of the underlying set of G, right? So if you just look at G as a set, the order of G is just how many elements are in the set. For example, the order of Zn is n. Right, there's n elements, 0 bar, 1 bar, all the way up to -1 bar. The order of the Rubik's group is, if I remember right, 11 factorial times 8 factorial times 3 to the 8 times 2 to the 12. So very big, but there's only that many arrangements on the cube. This is the order of an element. So the order of a group is how many elements the group. The order of an element is this kind of weird thing that looks like it's totally different, but it's not. And we'll talk about that later. A is the minimum in the natural numbers, such that when you do A to itself, do the operation that many times, it comes back to the identity. If no such n exists, then we say the order of the element is infinity. For example, look at the integers and take the element 1, right? 1 plus 1 is 2. 1 plus 1 plus 1 is 3. 1 plus 1 plus 1 plus 1 is 4, and so forth and so on. How many times do I have to add 1 to itself to get 0? It never happens, right? The order of 1 in the integers is infinite. How about in Z6? What's the order of 1 here? How many times do I have to add 1 to itself to get the identity? 6. All right, everybody agree with that? 1 plus 1, and that's the smallest you have to do. How many? What's the order of 2 bar? How many times? 3. Everybody agree with that? The order of 3 bar is. You can do better. You can do better. How many times you got to add 3 bar to itself to get the identity? 3 bar plus 3 bar is 6 bar, which is 0. So it's order 2. In any group, the order of the identity is 1. How about this? What's the order of this element? Call this X. 4. Good. 2, 3, 4. Do I agree with that? That's kind of silly. What about this element? XY. XY. Well, let me ask you this. How do I ever know that this is ever coming back to the identity? Right? How many of you think this? How many of you think that this ever will come back to the identity? It will. It will? What makes you think that? Only finally, okay, I agree, and that's very good intuition, but let me ask you this. Notice every now and then I get the cross, right? The white cross. Every now and then I get the corners, right? But what bothers me is, how do I know that I'm not in some kind of eddy, right? Like I'm in a whirlpool circling round and round. In fact, maybe there's the corners again. Maybe I've already done that before, right? How do I know that I'm not just stuck in some kind of loop that doesn't ever come out, right?
Its cube is a function, therefore it's 1 to 1 and on to.
Okay, I mean, I think you could kind of build that up into an argument. And of course, probably one of the best mathematical clues that this is going to come back is otherwise I wouldn't be standing up here like a freaking idiot turning this Rubik's Cube all this time, but there you go. All right. In fact, no matter what you do to a solved cube, it doesn't matter how complicated the move is. If you do it over and over and over and over enough, it'll come back. The move I just did, XY, it was order 105, which is strange, right? This only takes 4 times to get back, and this only takes 4 times to get back. But when you put them together in that just this way, it takes 105 times to get back. And notice 105 doesn't have any factors in common with 4. Right? Okay, any questions on that? Here's kind of another little fun fact about the Rubik's Cube. That's how many elements there are in the group. This is something like 4.3 times 10 to the 19th. The largest order of an element on the Rubik's Cube, they all have finite order. The largest element of the order on the Rubik's Cube is 1,260. So there is some combination that I would have to do that 1,260 times to come back. But given the size of this group, that's kind of a bargain. That's much smaller than the size of the group. Finally, the exponent of a group, the exponent of G, is the smallest n and n. This looks like the order, but it's a little bit different, such that a to the n is the identity for every a and g. If no such n exists, we say the exponent is infinity. Here, the exponent of this group is 6. That's the smallest integer. And if you take anything in this group and add it to itself 6 times, it'll be the identity, and that's the smallest one that works for every single element. The exponent of the Rubik's group will be actually some divisor of this. Yes?
Can you explain why it's 6 one more time?
What, the exponent? Well, so let's look at the orders of this. 1, 6, 8, 2, 3, 6. Everybody, I'm glad you asked that question. Everybody agree that those are the orders of the separate elements? Notice every one of these divides 6, right? Everybody agree with that? And so 6 will work for all of these, and there's nothing smaller than 6 that will work for every single element of that. Everybody okay with that? Notice that the orders of all these elements are divisors of 6. Agreed? And the order of the group, the number of elements in the group, is 6 as well. This is not a coincidence. We will see why that's true later. Okay. Examples. The first one, I am going to come out as sort of geometrically, dihedral groups. And dihedral groups are groups of symmetries on regular n-gons in the plane. Okay, let me start with a specific n to kind of help out, and then we'll generalize. Okay. You all have to give me a little latitude here and pretend that I can draw a regular pentagon. That's about as good as I can muster. Now, suppose I have a regular pentagon, all right? And I'm going to label these vertices here. So, now, my question is, I can rearrange this pentagon. I mean, imagine it's like a manhole, like you see, like a street manhole. I can pick this up and turn it 72 degrees and put it back down. I agree with that? Or I could turn this 144 degrees and so forth. So my question is, how many ways? Imagine that this is a puzzle piece, like you'd have like in a little 2-year-old's kind of shaking your shapes thing. Imagine you can pull this out and rearrange it. How many ways can I put that back in and make it fit? Everybody agreed that I can do it 5 ways just by, I can take that top corner that's its 1 now and I could turn it so it inserts at 2, inserts at 3, inserts at 4, inserts at 5. That's 5 different ways to do that. Everybody agree with that? Are there others? Look at that. She opened a whole Pandora's box. That's right. Another thing I could do is I could flip it, couldn't I? Right? So I could flip these two and these two essentially. So I'm rotating it around. If you imagine that this is a y-axis here, I can imagine rotating it around the y-axis, and that's another symmetry. And you can't get that one by spinning it, can you? Everybody agree? Okay, update. How many symmetries do we have now? I think symmetry is a way to rearrange a pentagon. It's you imagine this is a little child's toy or whatever. Okay, but I'm going to come at you again. At first, it was obvious there were 5. Then the observation was made you can flip it. So now it looks like there's 10. Why is there not more than 10?
There are 2 ways to lay a pentagon.
That's right. So imagine that I just pick this up and just put it back into this puzzle piece. One of these numbers, 1 through 5, is going to be the new number at the top, right? Do I agree with that? Let's say it's 3 goes at the top now after my rearrangement. What are these 2 pieces going to be if I've got 3 at the top? What do these ones have to be? One of them's got to be 2 and one of them's got to be 4, right? I'm just not sure which. And that corresponds to the flip, right? Everybody agree with that? So I've got, if I pick this pentagon out, I've got 5 vertices that I could put there. 5 choices for that. And then I choose whether to flip it or not. So multiply that by 2. So there's 10 ways to rearrange that. Everybody agree with that? So let R be, let's say clockwise. By or 72 degrees. That's the cut of your jib. And axis. I will list the 10 rotations that you get here. The symmetry 1, I mean, is an identity of the group. This is where I don't change it at all. I just leave it the way it is. I could rotate it 72 degrees. I could rotate it twice, rotate it 3 times, rotate it 4 times. What happens if I rotate it 5 times? What happens if I turn that? That's right. I get back here. Everybody agree with that? Because if I take that and turn it completely to pi, I'm back to where I started. Agree? there's half the symmetries. Those are the ones given by the rotation. What else can I do? Well, basically, I can add a flip after I do each one of these, right? I could rotate it and then decide to flip it, right? So in tandem to this, yes,
What does the first S represent?
S means, so for example, let's do this. Let's show what R cubed S does. One. Fine. So I'm gonna take, I'm reading this left to right here. So if I rotate this 1, 2, 3, that means my one will be down there. Agreed? So let me draw this little intermediate pentagon. 1, 2, 3, but 1, 2, 3. Right? That's just R cubed. But I didn't say R cubed, I said R cubed S, and then 2, flip it. And so that would result, I guess, in this. That makes sense.
So the first S that you listed is just when the one is still at the top, but the two is then in the fives place.
Right. So if you did S by itself, then yes. That's what it just flips it around the y-axis. Right. And this looks like a group under function composition, right? Let me show you how to combine things, but first let me do this. One other observation. What happens when I flip, rotate, flip?
You know,
See what happens here. Flip. Rotate. Rotate once. Who's going to be at the top when I rotate once after doing the flip? 2. Right, I'm going clockwise, so it'll be 2, 1, 5, 4, 3, and then flip again. That's going to look like this: 2, 3, 4, 5. Flip, rotate, and flip again. What have I effectively done to the original pentagon?
4,
What's that now?
4.
Right. I'm going to put it in a different way, but you're correct. I rotated it counterclockwise. Everybody agree with that? This is one of the fundamental theorems. So this right here these relationships govern the dihedral group. You have your basic rotation, R is rotation by 2 pi/5 radians. S is flipped about the y-axis. If you rotate for the pentagon 5 times, you get the identity. If you flip twice, you get back to where you started, right? And if you rotate, flip, it's going backwards. So for example, let me do a quick multiplication in this. Let me also point out that this is the same thing as, let's apply a flip here. Right? So we have this relation right here as well. So if I multiply RS, R squared, RS squared, S, R cubed, R, 4S. So if I do this in the dihedral group, what is it? I might come to regret this. Let's see. Can anybody see any way to simplify this? Okay, that's a great observation. What's S squared? It's the identity. So this is gone. Everybody agree with that? I've done nothing here. So I can abbreviate this R squared. Oh, and R squared, R should be R cubed. So this should be R cubed. That should be gone. This should be R4. SR4, SR. Okay, that's a little bit tamer. Now, I wanna use this to migrate stuff. Whenever I have an RS, I can turn things around. So this is SR inverse, R cubed, SR4, SR4, and I guess I can turn this one, no, SR. Are you okay with that? The R inverse kills some of this. Now, what else can I do? Well, I can keep migrating this stuff here, right? For example, RS is SR inverse. That's what we got from this equation here. So I guess my question now is, what happens when I get, let's see what is R squared S? It should be R, just put another R here, right? Do I agree with that? And now what can I do? Well, I know that RS is SR inverse. Do y'all see kind of a pattern? RS, I can swap these two out by reversing the exponent on R, right? R squared S is SR minus 2, right? I agree with that. And I can do another one. R cubed S is RS R minus 2, which is S R minus 1, R minus 2. So whenever I see a power of R with an S, I can just turn that around. That's going to make my life easier. This is R minus 2. This is SR minus 2. So I get S squared R minus 2, R4, SR4, SR. The S squared is gone. And these two cancel down to R squared. So this is R squared S, R4 SR. Do the same trick to R squared S. This is S R minus 2. And right. I got that in reverse there, didn't I? I did that right. This is SR minus 2, R4 SR. So this is SR squared SR. And we're getting there definitely. This R squared S is SR minus 2 times R. These cancel. And this is R minus 1, which in this case is R4 if you like. So doing this whole mess at the beginning is basically just turning this thing counterclockwise. Any questions on that so far, computation? In general, you have a dihedral group on any n-gon. All regulatory. So this is going to be kind of terrible. 1, 2, 3, 4, yada, n minus 1, n minus 2. No, I guess it would be n, wouldn't it? N minus 1. So if you have a regular n-gon, you could play the same game we did with the pentagon. Right? R is rotation clockwise by 2 pi over n radians, as opposed to 2 pi 5 that we did before, and S equals flip about y-axis. If the y-axis is here. How many symmetries do we have?
Times 2.
That's right. Imagine you've got n vertices here, right? So you've got n choices as to which vertice goes at the 12 o'clock position. N choices there. And then you only have to decide, do you flip it or not, right? So there should be 2n. And dn, we sometimes write it this way, is generated by rs, or when you rotate the n-gon n times, you get back to 1. You get back to the identity, the original position, right? When you flip it twice, you get back. And when you flip, rotate, flip, it's rotating backwards. What does this mean? This means all words with RS, R inverse, S inverse, subject to the relations above. What do I mean by words? I mean, just like this. It's a word made out of R and S, right? This is really R, S, R, 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 S, 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 R, R, 4 R's, then an S, then 4 R's, an S, and an R, right? You can also use R inverse and S inverse in making these words as well, but you're subject to these following constraints. Anytime you see N rows in N R's in a row, you can kill it. If you see 2 S's in a row, it can disappear. And if you see SRS, then it's R inverse, right? Or the way we wrote it, RS is SR inverse. Right? You might play around with this a little bit because actually it's kind of interesting because what this says is if you have all words made with these four symbols and you have these relations, there's only two N words you can make. Yes.
Have to have S inverse as a component, isn't that just the same as S?
It is. And in this case, you don't really need S inverse because it is the same S. But you should start off assuming that you need all of these, right? And then this constraint right here says, hey, I don't need S inverse because S inverse and S are the same thing. By the same token, for example, for the pentagon one, you don't need R inverse because you've got R4, right? So it's the same kind of idea. Other questions? Okay, so that's the dihedral group. I'm going to do something that's a little bit more all-encompassing, and later I'm going to show you how to sort of use this to get the dihedral group as well. Symmetric. This is a big example. And I'll tell you why I say it's a big example, because we're going to have a theorem later that says if you have any group at all, you can realize it as a subgroup of a symmetric group. So one can argue that group theory is over if you completely understand symmetric groups, because any group at all you can find inside of one of these things. They contain everything. Right? Let me tell you, the idea is not too bad. If A is a set, then SA, it's called the symmetric group on A, is the set of all bijective functions. I do need, let me throw in this. I want A to be not the empty set. And bijective is very important here. It's all functions from A to A that are one-to-one and on. So I could write this as set builder notation. Now, I'm going to specialize to an important subcase of this in a moment, but first, first of all, this has to be a group, right? Better be. Suppose you have a function from A to A. So let me kind of talk you through this a little bit. So suppose these are two bijections from A to A. What happens when you compose these functions? Isn't that also a function from A to A? Everybody agree with that? You go from A to A, pick it up where you left off, it's a bijection. And what happens when you compose two bijections? What do you get? Do I remember? Y'all remember that if you compose two one-to-one functions, the composition is one-to-one. You compose two onto functions, the composition is onto. So if you compose two bijections, you get a bijection. This means that we have closure, right? This is a binary operation. When I take F and G and compose them, I get a new element. This is in SA as well. Anybody think of a function that goes from A to A, that if you compose it with any function in either direction, it leaves it alone?
Yeah, I did it.
The identity function. The identity function does this. When you compose IA with any other function, it leaves it alone. Function composition is associative. Remember that from 3190, right? And here's another one. What happens when you have a bijective function? What's the big thing about bijective functions? They have an inverse function. Everybody agree with that? This is a group. The composition of two bijective functions, still a bijective function. You've got the identity function, you got associativity, and any bijective function has an inverse function that goes back, right? This is an honest to goodness group. And this is called the symmetric group on the set A. If A is finite, so if the set is finite, which in this class we will mostly be, when we talk about symmetric groups, we'll mostly concentrate on, say A is the set 1, 2, up to N, so a finite set like that, then SA is often written SN. Let me look at a specific example, and then I'll generalize. How about S3? By the way, how many elements are there in S3? How many bijective functions are there from the set 1, 2, 3 to the set 1, 2, 3? That's correct, right? Can you generalize that to SN? There you go. There have to be, it's got to be a factorial thing, right? Because think of it this way, what you're doing is you're making a function and you're going from here to here. And it's got to be 1 to 1 and it's got to be onto. So how many choices are there where you can send 1? There's 3 of them. Once you've made that choice, you can't send 2 to the same place you sent 1. Agreed? How many choices you got now? Now you got 2. And once you're down to last lonely person, there's no place to go except the one that's left over, right? 1. So there should be 3 factorial. Six, right? Now, let me do this here. I'll actually write these, as painful as it may be. Let's see if we can kind of intelligently write down all the functions. Anybody think of a way where I can sort of systematically write all the possible functions?
First to each, send the second to the remaining.
Okay, so let's do this. Right, that sounds good to me. I'm gonna call this F1. And what function is this? Can you identify it? This is the identity function, right? I agree with you. This is the function where everything's left alone. Well, maybe only one thing's left alone. Let's suppose that one's left alone. Well, if one's left alone, what has to happen to these other two? They have to swap because we've already done the identity function, right? So like that. Agree? I'll call this F2. If one's left, well, I'm out of that with one's being left alone. This exhausts my possibilities if one is left alone, right? But maybe two is left alone. I've already done the identity, so this would necessitate swapping these two. Right? And maybe three is left alone. And that necessitates swapping these two. Everybody okay with, we've got everything covered where everything's left alone and when only one thing's left alone, right? You can't have just two things left alone, can you? Right? Because with three things, that would force the last to be the identity. Agreed? So the only other thing is when nothing's left alone, right? And I might call this F5, and I might call this, what else could I do? One goes to three goes to one. Oh no. That three goes to two, and two goes to one. By the way, what is the inverse of F2? What do you have to compose F2 with to get the identity function?
Itself.
Itself, everybody agree? F2 is just a swap of two things. You got to swap them back to get the identity, right? The ones that I'm circling here, all those four, including the identity, are their own inverses, right? What do you suppose the inverse of F5 is?
Or, I mean, F6.
These two have to be inverses. And let's just follow it, shall we? What happens when we do F5 then F6? One goes to two, and then back to one. Two goes to three, and then back to two. And three goes to one, and back to three. Everybody okay with that? Now, so I've written all my functions, and I can make a little chart, and I can compose them that way. Everybody agree with that? Right? For example, if I wanted to see what's F2, F6, now, let's be careful. This means, this composition notation means I do F2 first, right? Where does one go? It goes to one and then on to three. Where does two go? It goes to three to two. Yes, you're quick. Yes, it goes two to three, three to two. So two goes to itself. And where does three? Oh, I know where three has to go. Yes.
I don't understand what you've done so far on that.
On this right here,
Yeah, can you like slow the steps down of how you're going from one number to the other?
I'm starting with one and I'm plugging it in. And to plug it into this, first I got to plug it into F2. So I say, hey, F2, where's one going? It's going to one. And when it's done, that output now plugs into F6, which is down to three. And there we go. Right? Is that cleared up?
Yeah.
I know the three has to go to one, but hey, it's me, so we better check, right? So F2, it goes to two, and then to one. Okay, so all is right. At least in 4120, right? Okay with that? So let's do a computation in S10, shall we? Nobody wants to do that, right? Nobody wants to. There's got to be a So I'm gonna introduce something called cyclic notation. I'll actually stop at 8. Here, I'm gonna do this example in S8. Now I'm just gonna make up some function here. That's just one function, right? I just picked that kind of array. Somebody tell me why I don't want to write all of them like I did in S3. How many would I have to write down? Oh, 8 factorial, right? I think that's like 40,320. Nobody wants to do that, right? But I've got a groovy notation for this. The notation for this, just kind of follow the cycle. Where does 1 go under this map? Okay. Goes to 3. Okay, pick up where you left off. Where does 3 go? 5. Pick up where you left off. Where does 5 go? Back to 1, right? So we close the cycle. This means 1 goes to 3, 3 goes to 5, 5 goes to 1. This is how this function works. The next number that is not accounted for is 2. Where does 2 go? It goes to itself. So I'm gonna just close it off there. Next number that's not accounted for looks to be like 4. Where does 4 go? 7. Where does 7 go? Back to 4. Okay. What's the next number not accounted for?
6.
6. Where does it go? 8, and 8 goes to 6. So I can write this notation this way, right? And some people would ignore the 2, just because it doesn't do much. Some people would write it this way. What this means is this function takes 1 goes to 3, 3 goes to 5, 5 goes back to 1, 4 goes to 7, 7 goes to 4, 6 goes to 8, and 8 goes back to 6, right? And 2 wasn't mentioned, so that means 2 just goes to itself. Okay. Now, remember how we composed this here by looking at the pictures? There's a quicker way to do this, and I'm going to show you how to do this computation here in S8 by objective function from set 8. So how would I do this? And we'll practice this more next time, but this is a good way to get some points on the test, I almost guarantee you. This is an element of S8. I don't know if I've used all the numbers, but I certainly haven't used anything bigger than 8. And you can think of this as, this is the function that takes 3 to 6, 6 to 1, 1 to 5, 5 to 2, and 2 to 3, and all other numbers between 1 and 8 that don't appear go to themselves. This is the function that swaps 2 and 7 and leaves all the other numbers alone. This is the function that swaps 1 and 8 and leaves all the other numbers alone, and so forth, right? Everybody okay with that? What's the output of this? Well, there's kind of a simple way to do this. This is just function composition. The important thing here is just being a good accountant, just kind of paying attention where you're at. I'm gonna start with 1. It doesn't matter where you start, but I'm gonna start with 1 because it's the smallest number. Okay? Just keeping track of things. We're composing functions, so we're going right to left. Where does 1 go? It goes to 5. There's no 5 here, so it's left alone. There's no 5 here, so it's left alone. Where does the 5 kick to now? 6. Where does the 6 kick to? 7. No 7. No 7. So at the end of one's journey, it ends up at 7. Everybody okay with that? Pick up where you left off. Where does 7 go? Left alone, no 7. Left, oh, no, not left alone. It goes to 2, right? And then to 3, no 3, then to 5, no 5. So it ends up at 5. Okay, you all tell me, where does 5 go?
Back to 5, right? Because it goes to 7 and 7 goes to 4. 1, okay.
Ah, controversy. Where does it end up?
1.
I think it's 1. 5 goes to 2. Into 7, left alone, left alone. 7 goes to 4, left alone, 4 goes to 1. That is correct. All right, what's the smallest number we haven't covered yet? We hadn't accounted for. 2. So let's do the dance at 2 here. 2 goes to 3, to 5, 2 to 4. Right? Where does 4 go? Left alone, left alone, left alone, goes to 1. Left alone, goes to 2. Closed off. I agree. Smallest number we haven't covered yet. 3. 3 goes to 6. Left alone, to 4. Back to 6. And that seems to be it. Where does 6 go?
1 to 8. Stays at 8.
It's 8, right? Everybody agree with that? We're out of numbers. So where does 8 have to go? It has to go back to 3, but let's gut check that, shall we? No 8, no 8. 8 goes to 1, to 2, to 3. Ding, ding, ding. There we go. So this whole composition of these functions here turns out to be the function that takes 1 to 7, 7 to 5, 5 to 1, 2 to 4, 4 to 2, 3 to 6, 6 to 8, 8 to 3. When you're done with this, when you do this kind of computation, which we will be doing in this class some, you should get cycles like this, and there should be no numbers shared. Notice there's no overlap between the 3 parentheses. Questions? We'll see y'all next time.
Okay.